So let's get started. So the overview of today's lecture is here. So I'll start with a recap of the last lecture, which is good because we have a few people who weren't here last time. And then we'll go over the concept of elastic moduli, and then we'll go over the concept of Moore's circles, and then we'll talk about how this applies to earthquakes and seismology. And then we will talk about real world examples. This is just my own research, and it's easy for me to talk about my own research, and in my opinion, it's interesting. So hopefully you guys agree. So let's go to the recap of last lecture. Does anyone remember what a stress is? Can anyone give me a good definition of a stress?
Pressure over a surface.
Say that louder.
It's a pressure or exert over a surface.
Yeah, okay, that's a good way to think about it. Like force over area, for sure, force over area. But what's the difference between a stress and a pressure? Because pressure is also force over area.
It's directional.
It's directional, exactly. Yeah. So it's a tensor. It actually has orientation associated with it. It goes to a certain direction. And the stress does the stress apply to the whole thing uniformly, or is it distinct at a location?
It's distinct.
It's distinct at a location. So it varies with heterogeneity and perhaps trends and bias throughout the medium. And it's at discrete points in the medium. And it has directionality. So we talked about the principal stress tensor, which is how you can orient your infinitesimal cube, which sort of represents how you're resolving those stresses in a certain direction such that there are no shear stresses. We all feel comfortable with that. There's just mathematically there's linear algebra. If Brian were here, he'd be talking about the linear algebra associated with that. But essentially, there always exists an orientation where there are no shear stresses. And so this is really useful for us in the Earth because these orientations have very distinct physical phenomena. Does anyone remember what SV is? The first one, SV?
Weight.
Yeah,
Everything above you.
Exactly. So it's the vertical stress. It's the weight just pushing down. And then SH max and SH min are very similar. They're the horizontal stresses. And they usually correspond to plate tectonics. It's usually plate tectonics, like the way that the plates move. That's what's causing these horizontal stresses. And there's always one in a maximum direction and one orthogonal in a minimum direction. Does anyone remember why there's always a vertical and two horizontal stresses? What's the reason for that? Why is the principal stress tensor always oriented like this in the Earth?
Air.
Yeah.
Air is a fluid.
Yes. Good job. So the reason I didn't think you would get that. So the reason is because air is a fluid, and fluids don't support shear stresses. A fluid cannot support a shear stress. It just, if you think about the physics of it, it just doesn't make sense. And so because of that, there's zero shear stresses at the surface, and so that must be a principal stress. Okay, so then we talked a little bit about laboratory testing, and we talked about how there's every time I step on that, the thing goes down. We talked about laboratory testing, how you can have a sample and apply a stress to it, and you can look at strains. We were essentially talking about how the strains are associated to the stresses. And we showed this curve, which I want to go into a little more detail now. What happens in each of these regions is really quite interesting. So there's the blue region here, the crack closing. So you can imagine you have a sample of rock. This is just rock. I'll even label it. And so in this sample of rock, like this is a rock that used to exist at thousands of feet of depth. And so it's got like, it used to be under very high pressure. And so when you bring it to the surface to test in the laboratory, oftentimes what happens is cracks open. It creates quasi-randomly oriented fractures. And these fractures exist throughout the sample. And what happens when you first start applying stress or strain, they're interchangeable. They're different, but they are related by the constitutive relationship. And so when you first start applying that stress or strain, you start closing these cracks. You start, they have a little bit of an aperture, and you start going like that, so they're completely flush. And then once you've done that with all the cracks, you get into the linear elastic region. In this linear elastic region is where all of the stress and strain is being supported by the matrix. The grains and the way that the grains are translating against each other, all of that is, or actually that's the next step. The grains just stationary, sitting there, feeling the load, feeling the strain and the stress. And that's a linear system. It's actually given by sigma equals epsilon. So the strain times an elastic modulus, which we're going to show in just a second, equals to the stress. And so during that portion, it's just a linear system. If you apply a set amount of stress, it's proportional to a set amount of strain. And then at some point you get into the elastic plastic regime, which is where it's still behaving somewhat elastically. So if you were to stop applying the stress, you would recover some of that strain. But now the grains are actually moving, moving relative to each other. So the grains are sliding past each other, cracks are forming, and the rock is just becoming more plastic. And the definition of plastic is that the strain is not recoverable. So you apply a stress, create a strain, and then you cannot recover that strain because it's plastic. And this needs to be jiggled. Okay, and so that's that region. And then once enough sort of like plasticity and concentration starts to occur, you actually get, actually I should back up just a second. These cracks start to open, the cracks open in the sample, and you get little seismic events. You get these tiny, tiny, tiny little seismic events that propagate throughout the sample. And you get one there, you get one there, you get one there, you get one there, you get one there. And eventually what starts to happen is that these events start to form a line through the sample. And then at some point, you get a shear failure. You get what is essentially a laboratory-caused earthquake. And those coalesced fractures create a shear through the rock. And that's essentially what happens in a triaxial system. Are there any questions about that? No? Okay. So that's just so what I just described here is something I wanted to describe in the last lecture, but I just either forgot or didn't have time, I'm not sure. And so I just wanted to go over that, and that's the end of the recap. So now let's get into elastic moduli. And it's a good thing we went over that because elastic moduli are very germane to this triaxial experiment. So the first elastic moduli that we'll talk about is the Young's modulus. So this is the equation I wrote here. Stress is equal to the Young's modulus times the strain. And you can also, so this is the strain here. This is the stress here. So the slope of this linear elastic portion of the curve is the Young's modulus, right? It's just the slope on E equals to the stress. The slope is the Young's modulus. So the Young's modulus is usually considered is sort of the first modulus we go to. It just seems intuitive to geophysicists, petrophysicists to go to Young's modulus. And you can think of it as just the stiffness of the rock. So if you have a rock that you put a lot of stress on it and you get a lot of strain, then that's a low Young's modulus. And if you have a rock where you put a lot of stress on it and hardly get any strain, it's a very stiff rock, it's a high Young's modulus. This is just a concept to describe the rock. It's a property of the rock which shows essentially stiffness. It shows the relation between axial strain and axial stress. The next elastic moduli we'll talk about is the shear modulus. The shear modulus is how resistant the rock is to shearing. And so we didn't talk about this last time. So last time we talked about strain, and we said that so if we have a rod with length L and we deform it to length delta L, the strain is equal to delta L over L, right? Now, instead of looking at it in terms of a linear sort of axial sense, we are instead going to look at it in terms of a shearing sense. So we have some element and we apply a stress to it, which we'll call tau. And so if physics works, tau will deform, will deform the block like this. And so the distance from sorry, I'm just trying to remember where the quantity is. So the distance from here, so if we call this distance here x, and this distance y, sorry, the nomenclature isn't quite perfect, then the to how resistant the rock is to shear stress. Okay, and then the next the next elastic modulus that we will go over is the Poisson's ratio. So the Poisson's ratio, actually here, let's sort of make a running list here. So we'll say G equals tau, and we'll just call this quantity gamma, tau over gamma. And so now the Poisson's ratio is the strain in the x direction over the strain in the y direction. And so what that means is if you take an element and you apply a stress to it, and there's axial strain, as we saw with the Young's modulus, what happens to the other dimension? Any guesses, any thoughts? So yeah, you have an element, you apply a stress to it, it strains, which is the epsilon x, and then the epsilon y in the other dimension. What do you expect the strain to do in the other dimension? You probably have some familiarity with this.
Yeah, it gets bigger.
Yeah, usually it gets bigger. Usually you apply a stress And you think about it, I wish I had like a ball or putty or something. If you apply stress to something in this direction, it gets bigger in the other direction. Usually, there are engineered materials that get smaller, which is pretty cool, but
So does that mean the Poisson ratio would be less than one?
it would be less than
I mean,
zero.
zero,
Less than zero, yeah. In that case, it's a negative Poisson's ratio.
Huh.
It's kind of
That doesn't
interesting.
seem right.
It's kind of interesting. In the Earth, we never see that. In the Earth, we always see positive Poisson's ratio, and it's always between 0 and 5. So, or sorry, 0.5, 1/2. So 1/2 means that if you apply an X strain, you get exactly as much, or is it exactly as much? There may be a coefficient I'm missing, but you get as the maximum possible Y strain. And so that's the case of like a ball. If you like a rubber ball, if you push that, it's got a lot of, it deforms a lot. In the case of 0, that means you deform it in one direction, but there's no change in the other directions, which is like cork. Cork is usually the example people use for a 0 Poisson ratio. Don't step on that. The next one we'll talk about, the last one. Sorry, I know this is a little boring. The last one is the bulk modulus, and the bulk modulus represents the resistance to volumetric strain. So if you apply a volumetric load or a pressure, for instance, in that case, you apply that load, that stress, you get a deformation, and that deformation is different depending on the rock that you're applying it to. Those different rocks have different bulk moduli, and I'm not going to write it up. The formula is shown there, and it's just the resistance to volumetric strains or stresses. And so one thing that's kind of cool is that if you know one of the elastic moduli, you know all of them. Or sorry, if I said that wrong, if you know 2 of the elastic moduli, you know all of them. So if you know any 2 of the elastic moduli, you can readily calculate all of the others. And so there are 2 moduli that we didn't go over, which is this, which is the Lemay parameter, or the first Lemay parameter. And then there's also the P-wave modulus, but they're much less intuitive in terms of how the system behaves, so I didn't go over them. So that's elastic moduli. That's just a very brief introduction to, these are essentially just descriptions of the resistance of the rock to some kind of exterior force, whether it's volumetric, whether it's shear, whether it's axial. It's just a measurement of the resistance of the rock to those forces. Are there any questions on elastic moduli?
What's the G again?
G is the shear modulus. So you see shear modulus as either G or mu. They're completely interchangeable. I have no idea why the community uses 2, but
Do you use mu more often or G? Like you personally?
well, in code I use G because code is so much easier to do G than mu.
Because I've only ever seen G, like in all my courses, it's always been G.
You've never seen mu?
No, not for sure.
Interesting.
Or maybe I.
No, I mean it's weird. I have no idea. I have no idea why the community has two nomenclatures. I don't get it. But I guess when I do code, I do G, and usually if I'm writing in text, I write out shear modulus. I don't think I usually put like G equals whatever. I'll usually say more along the lines of like the shear modulus is equal to. Yeah. Okay, so now let's move on to the fun part, more circles. So we talked a lot last time about the rotation of the stress tensor. Talked a lot about how that stress tensor can be changed to different orientations, what the different components of the stress tensor look like when you do that. And so now we're going to step away from thinking about rotating the stress tensor and now think about the physical element of a fault. So you have a discontinuity. We usually think of these as planes, just like completely flat and linear. But in reality, there's more to them, as if we have time, you'll see that later. So let's think about the stresses that are resolved on this plane. So you have a stress, you have a force acting on this plane. What would the shear stresses be on this plane? Yeah, exactly. And what does that imply? Exactly. So this is a condition of a fault that's experiencing principal stresses. And so if we just plot, bear with me here, there's going to be a reason for this. But if we just plot a diagram of normal stress on this axis, so we'll call this sigma n, and shear stress on this axis, we'll just call it tau. So tau is going to be equal to 0, right? What about sigma n?
Would be the value
Yeah,
of those.
exactly. Yeah, it'll just be the force acting on the plane. That's pretty simple. So let's call this, let's call it we'll call it alpha for some reason. So this plots, so alpha is the normal stress, 0 is the shear stress. So this point on these coordinate axes, and we'll get to these coordinate axes in a moment, is right there, right? We all agree on that? So what if instead of that fault, we look at that fault? So what about the normal stresses? What about the shear stresses? Sorry?
It's like the maximum value on this side.
Not quite, actually. No. So this point is going to plot, there's 0 normal stress, right? So the stress acting in this direction is 0. So the normal stress is 0. So normal stress is here. And then shear stress, I would argue there's 0 shear stress because you have to have some kind of some kind of traction. So it's what we talked about before with the tractions. If there's no traction, there's no stress. And if you were to take the traction of that force on that plane, because the force and the plane are parallel, there's no actual traction. So this point actually plots, right, and I want a new marker. Yes, exactly. That's exactly right. Exactly. That's exactly right. So this point plots right here, and let's call it beta. Okay, and now I'm going to show a third example. What about this point, or this plane? So this is the same stress field, just a different orientation of the plane in the stress field. Normal and shear. What are the normal stresses and what are the shear stresses?
Shear stress is not 0.
Shear stress is not 0, so shear stress is up here somewhere. Okay.
And normal is less than the first one.
Normal is less than this. What about relative to this?
Like bigger.
Bigger than that, exactly. So it plots somewhere over here. So I'll just put it right there. Why not? Ooh, this is a good marker. And that is, let's call it gamma. Just go in Greek letters. So these are those 3 stress fields. This is a plane plotted with those 3 stress fields. Or is it the same stress field, just different orientation of the plane? And so there's a mathematical way to think about this. Again, we're going to go back to our rock in the lab, just sitting there in the lab. And you can imagine you have a plane of some orientation within that rock, and this is just two-dimensional for now. I'm sure similar arguments can be made in 3 dimensions. And so there's just a formula, just given trigonometry, of how those stresses get resolved on that plane, depending on the angle that the plane has the horizontal. And what this looks like as a graph is this. And so this is the shear stress, and that's the normal stress. And the x-axis is the angle relative to the horizontal. And so you can see that this is one way of plotting this data, but you're going to see that this way is a little bit more useful. And so does that ring true that, you know, the shear stresses and the normal stresses, depending on the orientation of the plane in the stress field, are going to vary? And it kind of rings true to me that it would be sinusoidally. It'll be sort of trigonometric. But I hope it makes sense that there's certain orientations that, you know, for instance, at 90 degrees, the shear stress and the normal stress are 0. That's what we saw before, right? Shear stress and the normal stress are 0. And then other orientations, the shear stress makes maximum or a minimum. At different orientations, the normal stress has a maximum or a minimum. And they sort of vary systematically relative to each other. Does that feel okay? Yeah, kind of with me, kind of not. Okay, so now let's go back to these axes that I drew on the board. I'm actually going to make them a little stronger. That is the axis. Okay. So this is the same axis. I didn't put the points on there, so I apologize. I didn't prepare this quite correctly. But what do you think the possible stress states are? So do you think it's possible for the normal stress to ever exceed the 0 degree scenario? Can the normal stress on the fault ever be higher than the 0 stress scenario? No? Yeah, no, it just there's no I can't really explain it, but there's no reason why you could ever have more normal stress resolved on the fault than in the situation when the fault is exactly perpendicular to that stress. So we know there's no way the stress state can be in this orientation, in this section of the graph. Is there any way for the stress to be less than 0, the normal stress to be less than 0? Actually, let's go back to this curve. So can the normal stress be less than 0?
Brian asked you to share your screen.
Oh, oops, I didn't realize I wasn't.
Thanks, Eileen. I didn't want to interrupt.
Sorry, Brian.
Not a worry. Can you hear me? Thanks so much for doing this.
Yeah, no worries. So let's go there. Okay, so can the normal stress ever be less than 0? According to the graph, clearly not. There's no situation in which this curve goes below 0. However, I want you to think about that more intuitively. I want you to think about it in terms of, like, does it make sense for the normal stress to be less than 0? What would it mean for the normal stress to be less than 0?
The intention.
Exactly. So you'd have like an opening of the crack. And That's certainly possible. Usually in the earth, that happens with fluids. You inject fluids into the crack, you get tensile fractures. But in the case of just our laboratory rock sitting there with the plane, the fractures in them, there's no reason to ever suspect that the normal stress should be less than 0. So that means that the normal stress is contained right here. Right? It can't be less than B or beta, and it can't be higher than alpha. And so let's think about the shear stress now. Let's assume, I didn't draw right symmetric, but let's assume that this gamma is the highest possible shear stress. So this gamma corresponds to that point right there. So what do we think about the shear stresses then? What are the available shear stresses? I think that unshares my screen, if I'm not mistaken. So the shear stresses clearly have a range. There's clearly a range. There's a maximum shear stress and a minimum shear stress, right?
Does that happen at 45 degrees?
No, it doesn't. In this, it looks like it does. I think. Oh, actually, yes. The shear stress happens at exactly at 45 degrees, but the ratio is what we care about in terms of fracturing. And so the ratio of the normal stress to shear stress becomes most optimal at 60 degrees. Yeah.
Like you said.
Like what?
Like you said previously.
Exactly. It's part of the. It's sort of I think the word for that is Andersonian faulting theory, but that's kind of like a big catch-all term for a lot of things. So I'm not sure if that's the correct word, but exactly. So the ratio of those two becomes more amenable to fracturing at 60 degrees, but the maximum shear stress occurs at 45 degrees. And so. Yeah, so we're talking about the shear stress. So we want to plot all of the possible stress states. And I'm just going to plot it up because I'm not quite sure how to explain it completely correctly. But then the stress states are right here. It's a circle. Trust me, that's a circle. And so this is a Moore circle. This is a representation of all of the possible stress states, the shear and the normal stresses that can occur from different orientations of faults within the medium. And so in geomechanics, we don't ever really consider negative shear. We don't think about that. We usually just take the absolute value. And so for geomechanics purposes, this looks like this. Are there any, how are we feeling? How are we feeling? Are we doing okay? Doing well? I like the thumbs up. All right, sounds good. So these are the axes that we just drew a circle on. Essentially, all of that was just drawing a circle or even a semicircle. And oh, Brian gave a thumbs up, nice. And so this is a realistic representation of a Moore circle for a geomechanical problem, a geomechanical analysis. And you'll notice there's something a little different about this guy than our guy. Well, one is that the beta isn't exactly at 0, which is fine. There's the least principal stress does not have to be 0. And the reason why it was 0 in our case was because we were just applying one stress, right? We were only applying a single stress. So what do you see that's different between our circle and the one on the board, or the one up on the screen?
There are 3.
Yeah, exactly. There are 3. So what do you think? what do you think that is? What do you think is going on here? We said before that alpha and beta are principal stresses. We know that because they have zero shear. So what's going on? Anyone? 2 versus 3. Why do we have 2 and that has 3?
Drifting constant.
Say that louder.
Drifting constant.
That's a good way to think about it. So in the Earth we have 3 principal stresses. In the example I just showed, it was all 2-dimensional. So it's a dimensionality thing. So the 3-dimensional Moore circle has these sort of inner circles, and a 2-dimensional Moore circle just has a circle. And so when you're in 2 dimensions, I can't show this mathematically or even logically, but when you're in 2 dimensions, all of the possible poles, so a pole is a mathematical representation of the orientation of a fault. And so all of the possible poles plot around the edge of the circle. These are all of the possible stress states, all the possible fractures. And so in the case of a 3-dimensional Moore circle, this region here is where those poles can plot. Again, I don't have a mathematical or logical or intuitive explanation for it, but that's where the poles are. Okay. Doing well, everyone with me? All good? All good? Okay, and so next we're going to look at the influence of pore pressure. So if you so let's just assume that everything we've been talking about so far has been a dry rock. Now we're going to add pore pressure. We're going to add a pore fluid into the rock. What that does is it reduces what's called the effective normal stress. It moves that Moore circle over. And so now we're going to get a little mathy. And this is initial notation of the Terzaghi effective stress principle. So that so sigma ij equals Sij minus alpha pore pressure Kronecker delta. Does anyone know what the Kronecker delta is? The Kronecker delta,
Step function of sorts, right?
the Heaviside function is the step function.
Okay.
Delta is similar to the delta function, which is not this. The delta function is a singularity. It's equal to infinity at a point and 0 everywhere else. That's the delta function. This is the Kronecker delta. Sorry for the weird naming. So the Kronecker delta of Ij is equal to 0 if I is not equal j, and it's equal to 1 if I equals j. I think you need to have some understanding of i's and j's. This is what's called indicial notation. It's very useful when you start getting into a lot of like calculus, like derivatives and integrals and stuff, because you can keep track of dimensions very easily. And so so the I corresponds, so we're in 3 dimensions, so let's consider a 3-dimensional matrix, and I'll just call it A. So this is A11, A12, A13, A21, A22, A23, A31, A32, and A33. So it's very simple what an I and a J is. I is just the row, J is the column. So I is right here, that is I, and J is right here, that's J. So what does the Kronecker delta look? Oh, maybe I didn't. What does the Kronecker delta look like in matrix form? So if I is not equal to J, the Kronecker delta equals 0. So which of these elements are equal to 0? A2, 2. 8, so 2 is equal to 2. So that would actually be 1. So what you get is that the Kronecker delta, which is the initial, oh boy, and now I have to get Brian back on. Oh, maybe not, he still seems to be on. The Kronecker delta is equal to, in matrix notation, the identity matrix. We're all familiar with the identity matrix, right? If you multiply any matrix by the identity matrix, you return that matrix. So the Kronecker delta times the pore pressure times alpha. So let's go write this instead of initial notation, which is what I think the reason I put that is because I learned this in initial notation, but it's probably easier to think about it in matrix notation. So in matrix notation, we see that the effective stress, this is what's called the effective stress, is equal to the diagonal, because of the Kronecker delta. It's the identity matrix. So it's just looking at the diagonal. It's the diagonal of the original stress state minus alpha times the pore pressure. Just alpha minus the pore pressure on each of the diagonals. And what is alpha? So we know pore pressure. Pore pressure is a force over area, but it's a scalar quantity of force over area. It doesn't have a directionality associated with it. And it's the pressure of the fluid inside the rock matrix. So Biot's coefficient is what alpha is. Alpha is Biot's coefficient, and it varies between 0 and 1. And so if you think about it, 0 would mean that the pore pressure really doesn't matter, right? If you had an alpha of, oh boy, Brian, are you still there? If the pore pressure, sorry, if the alpha, yes, if the alpha is 0, the pore pressure doesn't matter. What does that mean about the rock? Think about the rock. What does that mean in terms of the matrix of the rock?
It doesn't have a lot of pore space.
That could be possible, and I'm sure there's a relationship between what you're saying is porosity. You know that word?
Yeah.
Yeah, so the porosity is related to alpha, I assume. I assume there's some correlation between porosity and alpha. But that's not quite what I'm getting at. I really like the thought though. No pore pressure would mean that pore pressure is equal to 0, not alpha equal to 0.
Oh,
Yeah. So what I'm trying to get at is the matrix of the rock is really stiff. It's not none of the compression or dilation or anything happening to the rock is being accounted for by the fluids inside the rock. It's just the matrix because the pore pressure doesn't matter. So if alpha is 0, the rock is just a very, very stiff, coherent matrix. And conversely, what happens if alpha is 1?
Not so stiff.
Not so stiff, exactly. So if alpha is 1, that means all of the pore pressure is absorbing that stress. That you're subtracting the stress with all of the pore pressure. And here's just a little table on lithologies to show that the different types of rocks tend to have different Biot coefficients. So salt is really ductile, it deforms really easily. You can imagine the pore fluid is going to play a very big role in that. The shale, also a little ductile, the pore pressure is going to play some of a role in that. And then as you get to carbonates and sandstones, where the stiffness of the matrix is stronger, the Biot's coefficient becomes lower, and the pore pressure plays much less of a role. And we already covered this.
can I ask something?
Mhm.
So for the field coefficient, it theoretically, I believe it's between 0 and 1. But in a lot of lab tests, it's larger than 1.
Oh, interesting.
Yeah, I've seen a lot of literature on saying that the field coefficient, you can see a lot actually larger than 1.2, 1.3.
Oh, interesting. I didn't know that.
In the lab tests, it's the reality is a little bit different, but if you look at the derivation of the alpha, it's supposed to be between 1 and 2.
Well, one thing,
Yeah.
one thing to keep in mind is that this theory, the effective stress principle, was developed for soil. It's not actually for rocks. The rock mechanics community just applied it to rocks.
Yeah, and then theoretically, the opioid coefficient is the ratio of the
It's compressibility.
Yeah.
Yeah, I did show that. I should have. Yeah.
So in soil, there is no bio coefficient?
No, there is. There is. Yeah.
There is
Yeah.
still,
Yeah.
On the-
It,
okay.
I think it plays more of a role because it's a small, that's probably not fair. But it exists. It exists for sure.
Because I first heard about I first heard about it in my rock mechanics class last year, but in soil mechanics in undergrad, never heard of the bio coefficient.
Interesting. I
Which
know.
is the standard, like,
Maybe
stress minus pore pressure.
maybe they're talking about like in the dry conditions, so pore doesn't play a role in that content. But once you get into like pore elasticity field, that's where Field's coefficient comes in, and the Skepton's B, those kind of coefficients comes in.
I don't know, Skepton's B.
Yeah, it's also related to Field's. It's in the pore elasticity region that they're all set of new other coefficients that's similar to bulk, Poisson-Young's, and shear. But they're for elasticity. So another.
Yeah, that's great. That's great. Thank you. Thank you. That's awesome. Yeah. Yeah. So that's just getting at the principle of effective stresses. And I have a slide later that'll illustrate a little more how this looks like in a fault, like what you can actually think about in a fault. But for now, I think we should take our break. So if everyone wants to stretch their legs, well, let's get back in I'd say 3 minutes. Just take a second, get some water.
The
Brian's applauding.
for the values of A, like respect of common rocks, like a medium to high.
Oh, yeah, you want me to put it back on?
Just like in question, like what makes the difference? Is it like porosity or near composition? What makes sense?
Oh, boys, there's so many differences between these different pathologies. So salt is very chemically different than the others. Carbonate is chemically different than the others. Shale and sand and stuff are chemically much
Yeah.
similar.
But like what makes the bio different?
I would, if I had to sum that up with one word, I would say ductility. I'd say the difference is ductility.
Okay.
Yeah. Eileen and Tina. Is Tina? Do more circles make a little more sense now to everyone? Or- Yeah, a little bit at least.
Okay, I'm trying to remember back to in geotech with like capillarity. How does that?
Capillarity is usually like a flow phenomenon. It's like you have pore space and like the size of the pore throat determines how much force slash pressure is required to get through it. I mean, I guess we're kind of considering static state for everything in terms of the flow of the fluids. The fluids are either there with pressure or less pressure or not there at all. That's kind of what we're thinking about right now. We're getting into, we're gonna venture into induced seismicity if we have time. And in that case, we definitely care about the evolution of pore pressure, which will involve capillarity because you have to get those fluids through the rock. I'd say capillarity is not a geomechanical. This is not a geomechanical. Yeah. All right, are we all ready? Yep, okay. So the next part of the talk is a little bit of seismology, no waves, no wave equation, no squiggles, no shear S, Rayleigh love, any of that. We're gonna be instead talking about the physical nature of a fault. And so this slide is probably misplaced, but it's important for what we'll talk about later when we get to the real world examples. If you imagine you have a volume of rock, this can be in the lab or it can be in the earth. You can imagine that there are numerous faults in that volume, numerous poles that plot on the Moore circle. And you can think of the faults in terms of their stability. How stable is that fault? Because you can imagine, as we were talking about before, if the ratio of the shear to normal stress is at a certain optimal value, you would expect that fault you'd expect that fault to experience shear rupture. And so the location in this diagram where the shear rupture occurs is this red line. This is called the failure envelope. I'll put it in our diagram. So the failure envelope can have several different forms. There have been different forms postulated by different scientists. And the most simple is the more cool, which is this linear version. And so the linear version says that the normal stress times mu, and I'll say what mu is in a second, is equal to the shear stress at failure. So the shear stress is equal to the normal stress times the coefficient of friction. Mu is the coefficient of friction, which can also be thought of as the tangent of right transferal, as the tangent of this, or the arctangent. Wait, tangent. Tangent, I think tangent of B equals mu. And so you can think of mu as how likely the fault, how amenable the fault is to slip. So if mu is really low, that means that the slope is really low. Yeah, question? Oh. That means that the slope is really low, and all of these faults are going to be past the failure envelope. They're going to be very favorable to slip. They're all going to rupture. The earth will shatter. All horrible things. And so if the mu is very high, this failure envelope is very high, and all of the faults are okay. So you can think of this as the coefficient of friction of the fault. How likely is that fault to slip given a shear state, given a stress state? Sorry.
I have a question.
Yes.
When you say slip, you mean stress, the shear fault, that or the normal?
So it doesn't matter between reverse faulting, normal faulting, shear fault, or strike slip faulting. It's just a matter of shear failure. So if you think about a material, it can fail in tension, it can fail in shear, or it can fail in compression. We usually think of a third one in terms of the modes, but there are different ways in which a material can fail. And in the case of the earth and faults, the failure, I don't want to use the word always, but it's almost always shear. And so when they reach that ratio of normal stress to shear stress, they fail in shear.
Yeah, so it happens all kinds of faults.
Yes.
No matter if it's normal or reverse or stress.
Yes. So yeah. So that's what this line is. And then I want to show also the concept of the Coulomb failure function. So the Coulomb failure function is a measurement of how close that fault is to the failure line. I like to think of this as the geomechanical stability of the fault. And so if we take this pole right here, the Coulomb failure function is the distance from the failure envelope. So how far away, the shortest distance from the failure envelope. And so I've color-coded all of these poles by their Coulomb failure functions. So you can see that the ones clustered up here are the darkest red, and they correspond to the ones closest to the failure envelope. This guy right here is the lightest green, and is the farthest from the failure envelope. And so in my research, which hopefully we'll get to, I'm not quite sure at this point, I use this probably a little too much, and so it's just a measure of how close that fault is to failure. How close is the fault to failure is the Coulomb failure function, and the Coulomb failure function this is the Coulomb failure function. It's just a measurement of distance to the failure line. Okay, and now I probably just dropped Brian again, and oh no, he's here.
I'm here.
Okay, thank you. So now let's get into what is actually resolved on a fault. Sorry, this slide was in the wrong place. I apologize for that. So when you think about a fault, I said before that we think about a planar. We think about something that's planar, but that's not true. It's not a perfectly smooth, infinite thing. It's got rugosity, curvature, roughness, and the roughness usually is the result of what are called asperities. So this right here is an example of a profile through a fault plane. So like if you imagine like a fault plane is directly at eye level, and how does the fault plane move away from the planar approximation? And so these points, the highs on this side and the lows on the other side, are called asperities. The contact of the fault of one side of a fault to the other side of the fault is specifically on asperities. It doesn't correspond to all of the area of the fault. In fact, it's only about 2 to 5, do I have them? Yeah. 2 to 5% of the fault is in contact with each other, and those are the asperities. And so if you imagine you apply stresses to the fault, and the asperities change, they have stress on them, they have strain, and what we observe is that the asperities are concentrators of stress. The stress concentrates in these locations. And so this is an example from Japan, the subduction zone, one of the subduction zones of Japan. And look at the scale here. So this is the x-axis and it's 60 kilometers. This is the z-axis, 20 kilometers. And so this is a big, big patch of the earth. And you see the shear stress concentration is right at these locations of high stress. And so the difference between the top figure and the bottom figure is before and after a big rupture. And so you can see in the case of this asperity right there at about 10 on X and 10 on Y, the stresses got distributed. They got shorn out over a larger portion of the fault. And so the stresses tend to concentrate at asperities. Oh, yes.
So these pictures, sorry, this is not a smart question, but these pictures, we're looking at it from the side, right? Not from above, like.
This is a cross section. But you also have to keep in mind that the fault is at an angle. So, okay. I mean, it's like a weird cross section. But it's not a dumb question at all. No. So yeah, the stresses get concentrated at the asperities, and then rupture occurs, nucleates at the asperity, and distributes the stress. It's called a stress drop over the entire rupture domain. So we're now going to get into the concept of coseismic and aseismic slip. So there's some asperities that are weaker than others, and some that are stronger. And the weaker ones tend to host what's called aseismic slip. They tend to just, you imagine you have to have a certain velocity of relative motion to cause seismic waves. And these events cause relative motion, but beneath that threshold, so there are no seismic waves propagated. This is called aseismic slip. And they correspond to the weaker patches, these little dark guys. And then the stronger patches tend to host coseismic slip. And what happens in terms of this is a numerical simulation of a rupture, and you see that over a certain period of time, this is the start of the rupture, time increases that way, and this is essentially just the changes in the stresses. And so you see the stresses start to change in certain locations, but it's aseismic. It's a bunch of little weaker patches failing, and then at some point you get enough failure. You get enough rupture on both weak and strong patches that you pass what's called the critical length threshold, and you get a coseismic slip, a big earthquake, not necessarily big, but that's how you nucleate an earthquake. And you start with these asperities. Some of them are small and weak, and those host a little bit of relative motion, and they slowly build up collectively to create a larger rupture that creates a stress drop across the entire fault. Okay, so this is just a schematic model of what I described. I like this paper. If you read one seismology paper this year, it should be McCormack 2019. So this paper shows 3 different schematics of how you might expect rupture to nucleate. This phenomenon that I'm describing, the asperities creating an earthquake, is called nucleation. And so this one is showing slow aseismic slip in the majority of the fault with little coseismic slips here and there. And eventually these nucleate into a big rupture patch. That's what I just described. Another model that this paper shows is you have a coalescence of co-seismic slips. So you have only the strong asperities moving through that medium. And then eventually you get a really big shock to the system, causes a big rupture, and that's an earthquake. And then the final is kind of a hybrid. It's a hybrid approach where there's like aseismic / co-seismic slip going on, and eventually you get a big co-seismic just sort of impetus, and that creates a large rupture. And then let's talk just a little bit about the difference between those co-seismic asperities and those seismic asperities. If you go into the laboratory and you control the velocity, so you have two pieces of rock that are sliding past each other. You have some apparatus that does it, maybe in a rotational sense, or like a rotary sense, or in just a linear sense. Regardless, you have two pieces of rock sliding past each other, and you can control the velocity of that slip. So if you go along at a certain velocity, you get a static coefficient of friction. The coefficient of friction that you observe is just static. And then you switch from that one velocity to a greater velocity. What we observe, and I can't give a proper explanation, but what we observe is that what happens to the coefficient of friction is that it jumps up really quickly, but then it starts to decay. And so if it decays to a position, and eventually after it decays long enough, it asymptotically approaches a value. And if that value that it asymptotically approaches is less than the original coefficient of friction, that means that the process of increasing the velocity caused the coefficient of friction to ultimately decrease. We call this velocity weakening. And this is the case of co-seismic slip. And so in the case of co-seismic slip, the slip happens, the velocity starts to increase, but the coefficient of friction also starts to decrease, which allows for that bigger earthquake, that co-seismic slip to happen. And the converse is true. So if instead of having the asymptotic value be less than the original coefficient of friction, it can actually be more. This is a velocity strengthening behavior, which corresponds to aseismic slip. This is the slip that is just sort of creeps, doesn't create seismic waves. Just in another word for it is creep. Another seismologists call it creep as well. And so that's just a little bit on the physics. This is called rate state friction theory. It is, if you want the name for it. Just a little bit on rate state friction, just to give you a sense of what's happening in terms of the friction of those co-seismic versus aseismic asperities. Okay, that was my little blurb on nucleation and fault composition. Are there any questions? Okay, so now we're going to move on to real world examples. This is my research, and oh boy, we only have like 6 minutes left. Oh boy. There's no way I can do this in 6 minutes. Let's open it up to discussion. Are there any questions about any of this? Anything in geomechanics, seismology, induced seismology? Anything at all?
Would you mind going back to where you had those three circles? Would you just re-explain what each one is?
Yeah. So these points, the point at 5,000, so 5,000 0, 6,500 0, 9,000 0. Those are the principal stresses. Those are the stresses that in the earth would be the vertical stress, the horizontal, and the two horizontal stresses. But in like engineering applications, they can be, I'm not an engineer, but those are the three principal stresses. And then the circles correspond to the possible stress states. So you can imagine you could orient a fault in however many orientations you want, but all of those orientations are going to plot in the region between this circle and the other two circles. So here.
What are the smaller two circles? What are each of those?
They're sort of void space is how I think of them. They're places where the stress state cannot. So it's a similar concept as the big circle. It's just an allowable stress state, but instead it's disallowing.
So if there weren't any like holes and it was like a completely like homogeneous surface or 3D object that was being put under stress, those two circles in the middle wouldn't be there.
I think in that case, so if there are no pre-existing fractures, there wouldn't be any shear stress,
Well,
right?
I think what it is it's based on your orientation, because we were looking at a single Moore circle looking at 2D. So basically, if you look at the principal stresses of the cube from like one angle of the principal stress, you're looking at one 2D thing.
Oh, that makes sense. 'Cause we've done Moore circle a lot before in our geotech stuff, and it's just one big circle. I guess I was confused.
Likely that's two-dimensional then.
Yeah.
If you don't have these two circles, it's two-dimensional. If you do, it's three-dimensional, and I don't want to hurt my brain and think about four-dimensional. Yeah. Okay, are there any more questions or discussion topics or anything?
I didn't quite get last time what traction was.
Yeah, traction's a little nebulous. It's a vector. So you should think of traction as a vector, like just, an arrow pointing somewhere in space. It's got a magnitude, and it's the result of the force on the surface. So the surface has some characteristic of like orientation, and the force is coming from another orientation. And you can imagine if the traction, or so say the surface is like this, and the force is being applied like this. Oh boy, that's not an arrow. The force is being applied like this. You can imagine that the traction here is going to be more like that, and the traction here is going to be more like that. It's basically the result of the force acting on a surface.
So if you broke up the force into components, normal and shear,
Um,
like the force perpendicular to the surface versus.
no, I think I drew this wrong and that confused you. One sec. Let me think of a better way to draw this. So the traction there will be like that. But then if you had a force like this, the traction would be more like that. So you can think of it like the force acting on a surface. So you have some force coming in, which is a vector. It's got an orientation and a magnitude. It's coming in on a surface, and the surface has an orientation. Say the surface is like this, traction coming in, or sorry, the force coming in, the traction is going to be a combination of the surface and the force vector. It's actually the normal vector of is the normal vector of the surface. I think it's essentially the dot product of the normal vector and the force vector.
Okay.
It's useful. So like this traction is something that like was developed in the 1800s or something, and they would use it to sort of build up their very like mathematically robust analyses of like the very fundamental stuff that we build all of this science off of. And we don't really use it anymore. I can't even remember the last time I saw a traction in a paper. Like I may have never seen a traction in a paper. Yeah, so don't worry too much about it, but essentially it's a very fundamental concept upon which a lot of other stuff got built. Yeah. But we really don't use it anymore. Yeah.
My other question was just about the 60-degree
Uh-huh.
thing came up several times. I didn't quite-
Oh, that's what we were talking about last time about how if you have let's do it more like that. So you have a maximum stress and a minimum stress acting on a medium. We'll draw a medium in there. And then eventually it's going to fail on shear just because of the stress state. And then the preferred orientation of that failure is 60 degrees. So this is 60 degrees from vertical. And as we saw in this figure, that's not actually the highest shear stress. The highest shear stress is at 45 degrees. But what matters is the ratio between the normal stress and the shear stress.
Okay, why is it that?
Why does that matter?
Yeah.
Because this happens in the earth, because we observe.
Well, I guess, why is it the ratio? That's the.
Why is 60 the critical ratio? Oh, why is the ratio important? Because if you think about it, a fault, if you have a whole ton of normal stress and a lot of shear stress, if the normal stress is too high, that fault's not going to move because it's just clamped together too much. If you relax the normal stress, even if you reduce the shear stress and relax the normal stress, you can get failure. So it's about the ratio.
Oh, okay.
Yeah. Yeah.
Thanks.
Yeah, absolutely. I think we can adjourn here. Thank you.
Thank you.
Yeah, thank you.
We got a quick question. If you
Sure.
got some time.
Sure.
So kind of trying to put this into injecting CO2 into the ground.
Uh-huh. That's what we failed to get to.
Yeah.
That's what we failed to get to.
Just based, I don't know, very fundamental. Like, I don't really feel like I totally understand all this, but you're going to increase the pore pressure,
Exactly.
which will reduce the normal
Effective
normal, which then leaves the door open for shear to take over and
Gold star.
have a little slip.
That's exactly right.
Oh,
Okay.
because we're changing the ratio.
Exactly. Exactly. Yep, that's exactly right. Yeah.
Okay, so it's
Absolutely.
bad.
Well, in some applications it's okay. In
Okay.
carbon sequestration, it's bad.
Okay.
Yeah.
But that's kind of just the most basic idea behind
Absolutely.
induced seismicity.
Absolutely. Yeah, usually when I give talks, I spend like 2 slides at the very start, that's just saying that.
Okay.
Exactly. Cool. Yep.
Always have pen catchable.
You're great.